All right. Good morning, everybody. Sorry it took a little bit for Kaltura to decide it wanted to record. All right. Before we start lab number 10, right, we have 2 labs. I want to see where everybody's at. So how many people are like completely up through 9? 1, 2, 3, 4, 5, 6, 7, 9. Okay, how many people are completely through lab 9? You're done. Awesome. So that's actually the vast majority of people. That's very good. Okay. Now, how many people have done the pre-lab for 10? Yeah, so. All right. Did you find it somewhat confusing?
Yes.
Okay. How many people read lab 10? How many people found that somewhat confusing?
Yes.
Okay. That's good, because I hate it. So I'm about to change the whole darn lab.
Yay.
Okay. And the reason is the way in which they got, I was told in spring that they were having a lot of problems with people having errors with this lab. And I read through the whole lab today and I just discovered why. So we're going to redo the lab in a different way because the way in which they're generating the counter is not wrong, but it's prone to errors. So we're going to redesign it in a simpler way that will have less errors. So they generate multiple counters and pass ticks between them and all kinds of stuff like that. And there is a way to do that, but you have to be very, very careful. Because if your timing is off a little bit, you get all kinds of weird errors that are hard to trace. All because that timing. Remember how I keep emphasizing in class? Timing is everything to us. So if we can force the timing to fit nicely, we're golden and everything works great. If your timing is off, you're in deep doo-doo. And what they run into is a timing issue when this happens. So I want to redesign it to kind of streamline our modules to make that work. Let me put this down. All right, so we're going to start by talking about what kind of the idea that I want to do for the way our counter works. We'll kind of draw where we're at, and then we'll build from there. So let me start with kind of the overarching idea of what we want to accomplish, and then that example will make a lot of sense. So let's go a high-level block. Oops. So right now you don't need anything download from here. We'll get to that in a few secs. Okay. So we've got a few things. Last time you built a calculator. I'm just going to call this calc. All right, this is essentially lab 9. All right, and that calculator, you know, I'm not going to worry about the specifics on this. It had basically some data that came in.
We're not quite focusing.
Oop, thank you. So this had some data that came in, and basically you could give it some opcodes. We'll get more specific here in a sec. All right, and the data and the opcodes ended up generating an answer. All right, again, don't worry about the specific wires. We'll get very wire specific. This is just high level. What's the idea? Okay? And you could do like addition and subtraction and or and XOR. I believe that was your 5 operations. And so this was kind of your calculator module. Now on lab 8, you had basically a 7seg 4 module. And it basically, as its output, gave you all the 7seg requirements, right? It gave you seg, and it gave you DP, and it gave you anode. All right. Now, what we really want to do on this one, last time you took the answer and some other stuff and you drove LEDs with it. What we want to do is have this come into, this is our kind of data to show, to display. And you gave it clocks and hex choices and stuff like that, but don't worry about that. We want to hook this up. And then we also had basically a digit selector. And that digit selector lets you see which one of the answers you'd be looking at. Because remember, any of these answers takes multiple digits. So this right here is fairly clean. Right? One big thing we're going to want to do is to build something to basically drive this digit selector so that it walks through and it counts 0, 1, 2, 3, and back to 0. And we want to do that fast enough so that it makes it look smooth, but slow enough so it has time to react. And let me show what I mean by that. If you've got an LED, all right, so let's just take a simple LED that's coming in. And we have current that flows through that LED. The output in light from this is going to follow a curve, right? So this is time. And from the instant at 0, let's say I let the current start to flow, the light that comes out is going to kind of ramp up till it eventually reaches a maximum. If you change it too fast, I turn on and then off, you'll stop it really low and you won't get a lot of light. So if your time period is too short, right, very small time, you're not going to get bright enough. So we want to kind of get up to here. Now, when you get up to this point, that light doesn't just disappear. It's going to keep showing for a while. So you kind of got this slow discharge of light. Anything above, say, this level would be good for people to see. So I've got time here before I need to kind of refresh it and hit it with more current to make it come up. So once I get to this area, I've got a time to switch to another one. This is actually a really, really slow slope. It would go way off the edge of my paper. It decays really, really slowly. So I have more than enough time to switch between the other ones. Now, if I go way, way too slow, it'll have become dark. That's the trade-off. So we need something that's going to count 0, 1, 2, 3, and put that into digit select. So if I'm going to build a module, it would be best if I just have 2 output bits. That is a signal that looks like this. And it's just slow. So rather than dealing with ticks or anything else, just think about this. We'll build a single module that will build this count. Does that make sense? And then I have to connect this data here. Now remember, our data here was a little bit weird, the way that we did this, so I'm going to have to modify this by putting in a new module to do some conversion here. But we'll deal with that in a sec. Because remember this one, we split our 2 8-bits, and we had 8 of it was like what was in the register, and 8 of it is the data that's coming out and stuff like that. So we're going to want to do something over here to convert that. And on top of it, this data coming out of here is a 2's complement number, and it could be negative, because I could do something like 0 minus 5. So really, I want to be able to take this and output data and the sign. And they don't even mention this part in the lab. So we're going to want to build basically 2 of these modules. We're going to talk about this one first. Now I'm going to let you go build it. And then we'll talk about this one. And we'll build that. And then we'll just hook it up. And then at the end, we'll have a nice, easy thing where you'll just completely use the already existing stuff and just hook the wires together. And that way you don't have to redo any of that. So when they talk about making a new 7-seg-4, that's crazy. You've already got a 7-seg-4. Just put the appropriate wires in. All right, so I don't want you to rebuild it, just make a new instance. What we're going to do is work to make these modules nicely drivable. Does the basic idea or goal of this make sense? Okay, so let me talk about what we want to do this counter that has 2 bits coming out. So I got to orient myself so the paper looks good. Okay, let's consider if I had a 3-bit counter. Well, actually, even let me just consider a clock coming in. And if I've got a clock coming into a D flip-flop. And my D flip-flop, all I'm going to do on this is I'm going to take whatever is coming in here, and at the moment, I'm going to invert it. And this one, without saying anything on here, we're going to consider it a positive edge. So if we look at our clock signal, off it goes. So here's my clock signal. Let's assume for a sec that my Q starts out at 0. Okay. So if Q is 0, what's the value on D? Well, this is a 0. That's an inverter, so what's on D is 1. So when I hit this, I hear it's going to see it, and Q is going to go to 1 because that's what's on D. Which means Q is now a 1, which means D is now a 0. But it can't change until I see the positive edge. Once I see the positive edge, it reads it in. Q becomes 0 and D becomes 1 again. So that will change again when I see the positive edge, in which case D becomes 0 because Q is 1. That's what the not does for me. And you'll see this pattern develop. Now, what's the relationship between clock and Q? Yeah, that's exactly. I mean, it just basically slowed it down. It looks like a clock or a count, just a slower one. Right? And it takes basically twice as long for that period. What happens if I did this same thing, except now I took it and I've got 2 of these flip-flops. And I'm going to put this 2-bit wire here just to indicate I've got 2, and they're hooked up in the normal way, right? A high bit and a low bit. And imagine I took Q and I wrapped it around and I went into an adder and I added the number 1. Does that make sense? So this is a 2-bit number. That's a 2-bit number. Right? We all agree? So when this sees a clock pulse, we've again got our clock. Whatever. Here's your clock. And then I'm going to have my Q. Maybe I'll write D. And let's say Q is initially a 0. Am I off screen? Oh, thank you. Okay, so Q is initially 0, which means what is D initially? I've got the number 0 in 2 bits coming around. It comes into an adder. It adds the number 1 to it. 0 plus 1 is 1. So it's in 2 bits. It's the number 1, 0, 1. We all agree? So then D, I can just draw as 1. And remember, when you're looking at your timing diagram, we have that kind of upper and lower bar, and we write the numbers in, which is basically just telling you read the bits in the normal order. So when I hit this positive edge, it's going to simultaneously read both of these bits of 1 in, and Q will change. And we do that change by locating the X of this. Means that's where the change happens. So you can time it. And what comes into Q is what was ever on D, which means the number 1. So what happens to D at that point? Well, Q is now 1. So what comes out of the adder? 2. Feel good with that? That continues up until the positive edge of the clock because nothing can change. At which point Q gets whatever's on D. And what happens to D? Okay, which is 3. Right. Positive edge of the clock. Q gets whatever's on D, so that means it goes to 3. And what happens to D? So here, this is where it actually gets a little funny, right? So I've got 3 plus 1 is 4, but 4 is 1, 0, 0, right? And how many bits do you have? So what's on D? 0. Remember, it's only got 2 bits. It can only hold those. It can't hold the third bit. So this has been our trick all the way through. I get back to 0 again. So this is 0, which means the next value of Q will be 0, and we will start our process all over again. So if you look at this, Q is counting 0, 1, 2, 3, 0. Well, what do you want? You want something that counts 0, 1, 2, 3, right? So if I built something that's going to count, and I take any 2 successive bits, I will get a signal. Now, so that's the whole trick. That's all I want here when I'm looking at this. Digit select, I want 2 bits. It's going to go 0, 1, 2, 3, back to 0. So I want 2 bits out of this counter. All right, so we're going to build a counter. That is a correct statement. But why pass out a tick or anything like that? Just pass out the top 2 bits. Now, I keep saying top 2 bits, right? The most significant 2 bits. Why do I say most significant 2 bits? Do I want a really fast signal coming out here? If it's too fast, what happens? It doesn't turn on all the way. So the whole purpose of this counter is to slow it down. Because how fast is your system running? Well, the clock on a base is 3 has anybody looked it up? It's 100 megahertz. Okay? That's really stupidly fast. Okay? Most of your LEDs, if you look, those things are responding kind of at a human pace. So your system is going to brighten up and everything else on a pace that's kind of handleable by you. How fast do monitors refresh images? 50, 60, sometimes you see a 70 megahertz or 70 hertz monitor. So it's doing this on the order of somewhere between, say, 50 and on the extreme side, 100 hertz or times a second. So let's say we even took an extremely fast one and just said 100 hertz. Our clock is 1,000,000 times too fast. So we've got to slow it down. So I've got to have a counter that's going to take that, 100 megahertz is like way down here. The bigger it has to count up, it's going to take a time to do that count. That's what we saw here, right? Every time I add a bit, it takes twice as long. All right, so if I add a 1-bit counter, my 100 megahertz clock becomes a 50 megahertz clock. I add 2 bits, my 100 megahertz clock becomes a 25 megahertz clock. Right? Each time it just takes twice as long, or you have the clock speed. So I've got to get this down to somewhere in that 50 to 100 range. Does that make sense? That's going to be the whole trick. And then once I get to that speed, I want it to count through 0, 1, 2, 3, and repeat. So I just want, from what we showed here, the 2 most significant bits, i.e. the 2 slowest bits. Because if you don't take the most significant bits, why did you have bits beyond that? The whole purpose of the bits was just to slow the dumb thing down. So we're going to make a counter. You don't know how big it is, so we've got to make it an n-bit counter. And we'll take the 2 most significant bits. Does that make sense as an idea? Now, it's always going to automatically count in our case. There's no reason to put an enable anything else on. We're just going to make it count. Because we don't care about phase shifts or anything else. We're going to pick the size of n. And this will be kind of your job. You're going to tweak it till it looks good by changing the size of n. And when you find it that it doesn't blink anymore and it's not, super dim, then you'll say, hey, that's my good value. And that's going to be one of the things you're going to tell us in that lab report is what size of n worked. So you'll guess a value of n, and you can roughly take an approximation of what that's going to be. And you'll try it. And if it's flickering, right, then you know that your signal is too slow. You went too far. All right, so i.e. your value of n is too big. And if it ends up being really dim, then you know that you picked a value too small. It's still too fast. So you got to increase n. That way you can kind of go back and forth and you'll know, and pretty soon you'll home in on a correct value for n. Does this make sense as a basic process? So we're going to want to pick n to be easily changeable. So how should we do that? We're going to pick a parameter. So our thing is just going to have a clock input. And it's just going to count, count, count. You'll have a parameter that will set how big it is that you can change easily. So you'll test it until it works. You'll output the 2 most significant bits, which will go into digit select. And that will cause it to flip between these. And then if it was me, I would just initially hook your data up to a switch. So you can just pick a number. And you don't have to worry about the rest of this stuff. So that you could just put some number in whatever you want, 5 or 7 or whatever, however you want that number to be, so that you can make sure. I pick something that has multiple digits so you can watch it pick through. Maybe you set them all to 1. I don't really care. Right? Something so you'll see the digits set up on there, and you'll make sure that it's a nice, clean, easy to read number, and you'll just adjust n until you get that. Okay, about how big do you think this should be? If we had to guess n, our number of bits, how would we do that?
Isn't it 100 meg over 2 to the n?
Okay, so the 2 to the n is going to be a number that you're going to count to. Okay? So we want 100 megahertz. Right. I want my 100 megahertz. And I've got this, I want to be somewhere around, either 100 hertz or 50 hertz, somewhere in that ballpark range. Right. So I have to divide this by my 2 to the n that you set.
Except, isn't it? Does it divide by the fact that it's doing 4 displays?
So this is going to, we want to get it into this refresh rate, and that's the approximate refresh rate. And I'm just trying to get you in the ballpark. Now, you're going to have that you're correct for the 4-1, so you'll have to slightly adjust your n because you're going to output the highest 2 bits. This is for technically the refresh rate for the sleep or the fastest bit of them all. Now, you can kind of pick n from this. Just reassign, rearrange this, take log base 2. You'll get an approximate value for n. And it will be approximate because you're correct on that. Right? But this should get you in the range. You should be able to try them and get an adjustment. This will give you your initial guess, though. You are welcome if you want to try to guess the formula in advance to get them all correct. But I'm just going to give you this as a test. Do we feel good so far? All right. So our plan, all right, this kind of gives you your initial guess of n for it. We're going to try to build this. So let's make our kind of initial circuit. So our initial circuit, we're going to have the 100 megahertz. Oops. Divide by 2 to the n equals somewhere around 100 hertz. And we will do your 7 seg 4. And let's say for our data, we just are going to pipe in, I think this data was what, 16? I don't have lab 8 on me. All right, you'll pick a number that you'll set on your switches to just hard input to this. The sign bit, just set to 0. We don't care about that. All right, we don't hex to des. We don't really care about that one either, right? It doesn't matter which one you pick. Pick one of them. All we're trying to do is take a look at the quality of the display. We don't care about anything else on here. So I'm just going to set, actually that's just some number 0. What we're really going to care about here is this last one, which is digit select. And that's 2-bit number. We're going to take our most significant bits. That's what I'm going to call those high 2. And I've got a clock input. And this is the counter you are building. Maybe I'll put n count, just to remind us it's an n-bit counter. And this is going to get clock. And this output will get, it has seg, DP, and anode, and you will hook those to their named values. You are perfectly welcome hard coding a number here. And you will just try ends until this works. So you have to build this module and then hook this up and try this until you get a good display. Does that process make sense to people?
So you'll want to just write a module for the end count and then make a test bench that instantiates both of those to run it?
Yes, you should instantiate the n-bit counter just to make sure it's counting. Right? So you always check anything new. The big thing you're going to want to see is that when you pick some value of n, that it counts through this. So, pick some reasonable value of n, and you'll show the leftmost of the timing and the rightmost of the timing where it kind of hits a high number, showing it wrapping around back to 0.
But what you're drawing for us is our circuit for our test bench, basically.
All right, so the test bench is just going to verify that this works. It counts correctly, and it will output the 2 slowest bits, the most significant. Then you're going to actually program it on your board.
Okay.
And you will try it for different size ends until you find the correct size end so that all of the digits displayed look nice. This setup will let you do that.
Okay.
Right? Because you put a number, whatever, I don't care, put all the zeros there. You'll get all the zeros across the digits. Doesn't really matter. You've already tested this. You're just trying to find out, are you twiddling these bits fast enough to get a good looking display? Does that make sense? You'll keep adjusting n. If it blinks, all right, then you know you got to speed this up. All right. So if it's too dim, you need more bits. You got to slow it down. So you'll increase n then. You'll just adjust n until you get the right value, which will cause this to look good to you. Do we feel good about this setup? Does everybody feel they know how to build this? All right, so when you don't know how to do something, what do? No, don't Google. Right? There are times Google is a good idea. Here's the danger if you Google. Right? Google is very useful if you know basically what the answer is, and you're like, I just don't want to waste time writing all this junk. That's a great use of Google looking for code. A bad use of Google is, I have no idea what to do. What should I do? And the problem is, you don't know if you get quality or not. If you kind of know what you want, you can look at what they did, and you can look at it and go, yeah, that's a reasonable idea. Or, no, that's garbage. Right? But if you don't know, you will get messed up on it. Second danger to Google. When you go working actually out at a company, there are things that we call poison pills in code you find on the internet. And the poison pill is primarily this. You might not be expecting it. It's a legal thing. Many open source codes actually have a legal requirement as part of their open source licensing. That means any derivative code must also be open source. Most companies and government agencies and things like this do not want to have all of their intellectual property out there on, the internet free for everybody to use. And if they don't, they're in legal trouble according to U.S. courts. So if you incorporate that code directly from there, you have basically damaged your company's standing to be able to legally defend their intellectual property. Far beyond just the code you did. Some of them actually have such a hazardous licensing thing that any code that's involved that gets in there becomes open. So even things that were not related to that become potentially viewable. So that's why the other reason you have to be really, really careful. There is a big legal danger with all of these. So draw the picture, right? What do we say a counter is going to do? How does a counter function? Like if you count, like imagine I'm like a 4-year-old. I'm like, how do you count, right? What would you tell me? Just literally at that level. What's counting? Okay, so I would start with the number and add on, right? And what number do we want to start with? 0. So I should probably have available to me a reset so I can start the whole thing, right, at some 0. And then I'm going to have a count. And that to count to add 1, what circuit allows me to add 1 to a number? An adder. So I can do an adder. So I'm going to need, inside this unit, I'm going to need a certain number of bits, which is a D and to a Q, right? How many bits do I need? Well, it's going to be whatever you set it as, right? Which is n bits. You're going to pick n, and that's how many bits are there. How do I do the counting? That's what I need to do here. Remember, right? So we have our memory units, and I need to take something that's going to take Q as an input, and it calculates D. So how do I go from Q to D? N-bit number Q, N-bit number D. I have to done. Add 1, which is an adder. What's our symbol for an adder? It's this kind of funny notched mux, right? And we usually put the plus on it. And what do I want to add to it? 1. How do I write that in Verilog? That's the circuit, right? How do I write this in Verilog? Well, I have to name this wire, right? And we said this is usually called like Q next or something like that. All right, and this one can be called a bunch of things. All right, it can be called Q current. It can be called Q reg. It can be a lot of stuff. I'm going to use Q reg. So if I look at this, how would you describe this circuit. Q next,
Yeah, but
Q next,
would that just be Q-next, or assign Q-next equals Q-reg plus 1?
boop. That would be totally fine. And then I'd have to make both of those wires of the appropriate size. I mean, that's literally all you have to do. Right? They make it sound so much more complicated the way they do it on theirs with all kinds of enables and ticks and everything else. Literally, all you're doing is you're adding 1 to the previous number. So that's all we're going to say. Add 1 to the previous number. Now, because the software has all kinds of adders built into it, it's going to pick different adders, and it will find the one whose timing will finish in our clock time. So we're just going to tell it, look it up amongst all the adders you can build, find me the one that works. That's what we're telling it to do. So it might take it a little while to chunk through that, but what do we care? That just takes a little longer to simulate, a little longer to build, but in operation time it runs great. So we're going to leave it to do that job. And then all we have to do for this is then hook up a clock. And how do I do my reset? Well, that's inside the memory areas. We've already built a register, right? So remember in class we built a register? So this, we have a reset. So if you remember the way we ended Monday's class yesterday, we had built that thing and we said we've got the part that is the register part, which has the, always at, right, pause edge, clock, pause edge, reset. We did that part. We said that's going to basically stay the same. The only key difference there is QReg is going to be the name of our variable that's getting assigned. QReg will get whatever QNext is when it's a clock pulse. At any other time that it's being triggered, it must have been a reset, right? So we'll check and see, is it a reset? We'll set it to 0. Otherwise, QReg gets QNext, and you already know how to do QNext. This is literally like a 4-line piece of code. It'll be very, very short for you. And it'll do everything you want. You'll just check it, and away you go. The output from this is going to be the 2 most significant bits of this. So you'll also need to assign to whatever you call your output. Do not make your output QReg. Right? You have to have some other output, MSBs, and you'll have to take the 2 most significant bits of QReg and set that as your output. Does that make sense? Okay, build it.